Good day, everyone. I am Nelvin Quaton, together with my thesis partner, Juven Yangson. We are students from Caraga State University taking up Bachelor of Science in Electronics Engineering. We would like to present our research work entitled Design and Development of a Low-Cost Ventilator Machine with the advisory of Engineer Edgardo Ricardo B. Sahonia Jr. For the outline of the presentation, we will discuss about the introduction, the objectives of the study, methodology, results and discussions, conclusions, and lastly, the recommendations. Mechanical ventilator plays a big role in medical sector. It is used to ventilate patients with severe problem in respiratory and experiencing difficulty in breathing. However, a shortage on this machine is one of the major challenges in every hospital, especially in developing country like Philippines, particularly here in Caraga. It's because of different factors like having a high cost per unit and also a dramatically increase in patients that needs to ventilate, like in what had happened during COVID-19 pandemic. To develop a low-cost ventilator is highly needed to meet the high demands for this kind of machines. So here are the list of common mechanical ventilators that been used in different hospitals. The price range is around from 100,000 to 100 million pesos per unit. It varies depends on the brands and in the complexity and operation of the ventilator. For the objectives of the study, our general objective is to design and develop a prototype of a low-cost ventilator machine to assist the needs in the medical sector. And for our specific objectives, the first is to design a prototype of medical ventilator with automated ambu bag pumping. And second is to develop a medical ventilator that has lesser cost compared to the conventional mechanical ventilator. Introducing the methodology that we conducted for the implementation of the study, it involves the following. First is the design and development of Raspberry Pi-based hardware components such as the microcontroller, sensor, stepper motor, touchscreen display, ambupressor assembly, and etc. Followed by the development of Python 3 script for hardware interfacing with touchscreen display and slider control. Then next is the integration of all hardware components and software, and also testing. Lastly is the accuracy assessment and evaluation of the machine. Here is the system overview for the entire operation of the machine. First is the Raspberry Pi will send the user input parameters or the data to the Arduino Mega. Then the Arduino will control the stepper motor based on the received parameters, in which will cause the pressure to press the ambu bag. Then the delivered oxygen will travel to the breathing circuit wherein the PIP valve, the HEPA filter, and the flow sensor were attached before it reached the patient. This feedback mechanism from flow meter or the flow sensor will be available during assist control so that the ventilator will provide another volume of oxygen that is triggered by the patient. This flowchart shows the sequential operation in controlling the ventilator. As the start button is pressed, the ventilator will operate in the default parameters in VC-ACV mode. Then the stepper motor will rotate, causing the pressure to compress the ambu bag. The user can also change the mode of operation, either VC-ACV or the assist control, and the VC-CMB for the continuous mandatory control, as well as the parameters. In VC-ACV mode, the flow trigger is activated. So during expiration phase, if the patient attempts to breathe, the ventilator will provide another set volume of oxygen that is synchronized to the patient breath. Then if there's no another breath initiated by the patient, the ventilator will back to the set frequency in the machine. In VC-CMV mode, it has the same operation in VC-ACV, but the difference is it has no flow trigger, or the flow trigger is deactivated. The control has also a reset, stop, and also a start or resume buttons. Here in this slide, it shows the whole circuitry of the ventilator. On the left side, it shows the interconnection of the Raspberry Pi, Arduino Mega, LCD screen, and speaker. While on the right side is the schematic diagram in Arduino Mega, in which the driver of the stepper motor and flow sensor are connected. Also, the exhaust fan is connected to the 12 volts power supply. Here is the whole design of the machine and sizes of our supports, gear, and pinion, and the pressure of the ambuba. This is the GUI and controls we created for the ventilator. In left side is the VCA-CV mode, while VC-CMV mode on the right side. The difference between the two is that the flow trigger is activated during VCA-CV mode. Then the GUI have also a 4 sliders for the 4 parameters such as the tidal volume, the breath per minute, the IE ratio, and the flow trigger. By the way, the available range for tidal volume is from 300 to 600 ml. For breath per minute is 10 to 25, 10 to 30. And for the IE ratio is from 1:2 to 1:4. And for flow triggers from 1 to 5 liter per minute. The set parameters will be displayed in the upper right side of the GUI. This is the table for the manually gathered data and estimating the number of steps of the stepper motor. So we had the set tidal volume and also the I time or the inspiration time that can calculate using this formula. And for the flow rate, that can also be calculated using this formula below. We estimated the number of steps for the stepper motor by basing from the actual reading of the flow sensor that must be approximately equal to the calculated flow rate. So by applying nonlinear regression to this table, we formulate an equation for the number of steps. This is the summary output of the regression. Since all the p-value of intercept, tidal volume, I time, and flow rate is below 0.05, we determine that these are all significant values in calculating the number of steps, including their coefficient. Therefore, our formula for the number of steps is this equation below. For the results and discussion, here's the photos of the actual ventilator and the breathing circuit. We can see the LCD screen with the displayed GUI and also the flow sensor that is attached at the end of the breathing circuit near the patient to read more accurate volume of oxygen that is delivered to the patient. Next is the circuit of the ventilator. So we had the Raspberry Pi and Arduino and other components. The overall cost of the materials that we used for constructing this ventilator is around 30,000 pesos, this including other parts like the exhaust fan, speaker, and etc. This figure shows the variation of oxygen graphical flow from the 4 out of 30 experiments we conducted. They have different maximum reading of flow because of different set of parameters that we can see on the lower right side of the figure. Here is the table showing the results from the 30 experiments we conducted. Each experiment have different set of parameters. We can also see the column for the expected flow rate that is manually calculated and also the actual flow rate that been read by the flow sensor. The experiment number 3, in which all parameters are set in their lowest value, it gained the maximum percentage error at 11.11%. The actual flow rate had a reading of none greater than plus and minus 3 ml from the expected flow rate. This is the graph that shows the comparison of expected flow rate and actual flow rate and also the percentage error. So these are our conclusions on our study. First is using a two coordinated microcontrollers, Raspberry Pi 4B and Arduino at Mega help to avoid interruption in delivering sufficient volume of oxygen. Second is the ventilator could supply a given volume of oxygen with a maximum inaccuracy of 11.11% based on the results. Then third is the conventional mechanical ventilator cost more than 100,000 pesos per unit, while this prototype will cost only 30,000 pesos including machines minor parts, with an estimated final product cost not exceeded 60,000 pesos. So here are the recommendations. First is to add another mode of ventilation like a pressure controlled ventilation. So by this mode, an additional sensor is highly needed, such as the differential pressure sensor. A graphical flow could be also included to the graphical user interface. An integration with backup power supply to the machine, which could make the ventilator will be operational for a long hour in case of power shortage that is common in rural areas. The size and dimension of the ventilator can be resized to a higher dimensions, especially the rack and pinion to a more range of volume that the ventilator could deliver. And lastly, further studies and testing are also recommended to make the ventilator more accurate in delivering a volume of oxygen and have its certificate of calibration standard based on ISO TC121 SC3. So I will show to you the actual video of our ventilator. Here is the actual video of our ventilator.
BCCME mode is activated. Ventilating the patient. Volume 500 breaths per minute. 21 patient. Volume 600 breaths per minute. 13 rating 1 2 2. Ventilating the patient. BCAC mode is activated. Breath per minute. 21. Low
That's the end of our presentation. Thank you.